from discussion leaded by Farah today. Then class begins with myself and Sunghan. We have a lecture. I guess we can finish up earlier so Juno can continue the discussion. So we can do 4 things today, hopefully. Right? Okay, come on. Come on. Which device do you want to use? This one? Yeah, this one.
Where was the discussion?
Class, and also I hope we can do discussion again. Right. Because we left discussion there. Because of time, it is delayed.
Yeah. Because discussion 먼저 하는 거야. Last, mine was to happen last time. Yeah. But on Monday, that's why there was not enough time.
So we start from discussion.
Yeah. No, I'm gonna use my email. You have to send discussion theory. Like, in YouTube. I didn't know. Should I send it now?
I'm reading old version.
I don't know where it down.
What version is it?
Right? Yeah.
Yeah, you are right. You are the discussion. Yeah, today. Right. Okay. Forward. Okay. Juno is next week, right? 이쪽도 쉐어를 해야 될까? 네, 맞습니다. 쉐어를 오늘 교수님 나중에 거기 쓰신다고 체크하려고 하는 거니까 얘기가 왜?
뒤에 있어, do it.
잠시만. It's check his devices. Yeah. Complicated system.
format. Today I'm going to lead the first discussion session. So our topic is subsea. So our topic is subsea production system. So first of all, why do we need this subsea production systems if we have these offshore platforms? Like, what is the purpose of this subsea production systems? Can you tell me that? Why create them? Anyone?
So they hire oil.
No, like that's basic. But we have offshore platforms. They also get oil, right? Like, why is there a need for creating these subsea production systems? Like logically, what can you say? So, if there is no answer, you know the answer. So, a subsea production system provides a way to produce hydrocarbons from areas not economically or easily developed by the use of offshore platforms. So, with field development targeting deeper and deeper waters and more remote areas, there is a need to put as many components as possible of these hydrocarbon facilities on the seabed. This seems like the best economic solution. And why we need to go deeper and deeper, like in terms of the depth of water. What is the reason for that? Like it was mentioned in the last lecture. Yes.
Because we have less and less resources.
Yeah, like offshore reserves that are close to in shallow waters, and the land reserves are being depleted. That's why there is a need to go deeper and deeper, and more remote areas. So, can you name me some of the components of the subsea production systems? Just what comes to your mind? Yes?
Drill.
Yeah. Drilling systems, and then anything else? Nothing? Yes?
Wells.
Yeah, wells, wellheads. Okay. So these are some of the systems, like drilling systems, wellheads, subsea Christmas trees, umbilical and riser systems, control systems and instrumentation, tie-in and flow line systems, manifolds and jumper systems. These are some of the systems, and this really seems confusing, and like the names don't tell much. So I'm going to show you some pictures. Can you guess which one is what? Like the left one from your perspective and the right one. What is the left one? Yes?
A wellhead.
Yes, right. It's a wellhead. And the right one? Yes.
Christmas tree.
Yeah, right. So can you tell me what does wellhead do and what does Christmas tree do? What's the purpose of this? So wellhead, the left one, the wellhead is a pressure-containing component that is placed on the surface of the well, and it provides interface for drilling, completion, and testing of all subsea operation phases. And the right one is the Christmas tree. It is an arrangement of valves, pipes, and fittings and connections. It is placed on the top of the wellbore, and it provides interface between the wellheads and flow lines. Right. So let's move to the next pictures. So what about this one? The left one and the right one. What is the left one? Anyone? No one? Okay. Left one is manifold. So what does manifold do? Production manifold is a structure containing valves and pipes, pipework that is designed to commingle and direct flows from the wells into one or more several flow lines. So it is designed to combine, distribute, control, and monitor the fluid flow. And what about the right one?
Can you provide any options to choose?
options. The names. Okay.
So that they can choose.
Okay.
It's more easier. Right?
Umbilical or jumper. No. Nothing. Like this one. Okay. It's a jumper system. So jumper is a short pipe connector that is used to create interface between two subsea components, like manifold and manifold, manifold and Christmas tree, and or manifold and export sled. So okay, this is the last one. This should be easy. So what is this one? I've mentioned this. Okay. Pardon? No. Yes.
Umbilical cable.
Yes, right. So it's umbilical. So we can see. So what is the purpose of this one? So we can see like there are several pipes and tubes inside the outer sheet, and so what's the purpose of this? So what does it do? Yes.
Provide electricity.
Provide what?
Electricity.
Electricity, and what else?
Water. No. Oil. Provide oil.
Not exactly oil. So, like these cables, each one of them carries something different, right? So we've mentioned electricity, electric power. Like there is also hydraulic power, and there is sending electrical signals, right? And then there are fiber optic cables for short distances. And then there is also injection of chemicals for subsea injection and for supply of gas for artificial lift. So and these cables are protected by an outer sheet, like casing. So then, can you name me a few challenges associated with subsea production systems? Whatever comes to your mind. Yes.
Interventions are difficult.
Pardon?
If there's any issue, interventions are difficult.
Right, right. Anything else? Yes? Yeah. Anything else? Yes.
It's hard to build in the first place.
Right, right. Okay. Anything else? Nothing? Like what I meant, like everything is right, but what I meant by challenges, it was more like fundamental issues, like what causes all these things that you said, like to the core. What are the issues? Yes. Pardon? Corrosion. Right. One of them is corrosion. What else? Nothing. Okay, I'm gonna start with showing like high pressure, obviously, right? Like it's deep sea environment, so we have high pressure. So what does high pressure do to our subsea production system? So due to high pressures, the subsea systems are constantly under critical and complex loadings. So, right? If we have pressure, what else do we have? Obviously, pressure and temperature, right? Large temperature gradients. So, what kind of problem does this cause to us? Like, we have temperature gradient, right? What else? Like, what happens?
Stress of the structures.
Yeah, kind of, but yeah, I guess that's also right. But what I've found is that so when the oil comes to the seabed from the reservoir, it's obviously hot, right? But the seabed water on the seabed is cold, so there is large temperature gradient. But we need to maintain the properties of the oil, the fluid that comes from the reservoir, right? But when there is this kind of temperature difference, it's really hard to maintain the properties of oil. They can change, and when they change, it's bad for us because we lose energy, right? So so the oil will become colder in the flow lines,
And that's why there's a need to insulate the pipes in order to stabilize and maintain the temperature for maintaining their old properties. Okay, next one is seabed conditions and topography. So what can you say about this? Like, why? I'm gonna say one sentence, and you try to continue. So the production system and the pipeline route selection is one of the more critical activities. If it is done poorly, without taking care of the geotechnical and marine conditions, it may be costly and result in operational delays. Why? Like, this is related to this, the latest the seabed conditions and topography challenge. So, okay, I'm going to give you a hint. So, in space, when the low Earth orbit, right, we have satellites. When they collide, what happens? There is creation of what? Yeah, right. So we also have the same thing, like not exactly this same kind, but like we have debris. It's like if the seabed is uneven, there can be accumulation of debris on the subsea production field. So, and that poses an issue for us. That's why, as a result, it may be often necessary to remove this debris from this place. And it's important to remove this debris from places where the important structures like umbilical and pipelines are located. So that's why we need to select the proper route for our structures in the subsea production systems in order to avoid this marine debris. Next one, salinity, right? Obviously, she mentioned corrosion, so salinity is like one of the roots of corrosion, right? So, exposure to salt in the sea environment causes equipment to deteriorate. Oxygen in the water reacts with salts, and it causes pipelines, risers, and any equipment to corrode. Next challenge is location factors. Can you name me something? What is related to location factor? Like one example. How can location be a challenge for us? Like this is a bit different from other categories. Those are almost always happening, but this one is like particular for each location, right? So, an example?
You can't choose where the oil field will be, so there's a volcano nearby or undersea volcano nearby.
Yeah. Actually, it's a good example. My example was Gulf of Mexico. So there are hurricanes in that area. So the engineers have to design so that they can take into account these conditions that are brought by hurricanes. So this is like similar example. That's right. And then buildup of solid depositions. So the buildup of wax, scale, hydrate, asphaltene, sand. This is also an important issue for us because due to temperature gradients, so this our oil is temperatures are low and the flow is unprocessed well stream. So due to these conditions like low temperature and pressure, like there will be solid depositions. Like I said, wax, scale, hydrate depositions, and it's also important issue because like when these things form, they are formed from the fluid, right? And so we lose, like we can't deliver a proper flow, and we lose substance. Next one, corrosion. It was mentioned. So we move to our next topic. It's corrosion. So, what is corrosion? Yes? Pardon? Yeah, right. Corrosion is the process of decay on a material caused by a chemical reaction with its environment. The reaction is usually oxidation. So next, like before the next question, I want to ask, when we say corrosion, we usually think of metals, but does it always happen to metals? Mike, can you answer? Does corrosion, okay?
No, it usually happens to a specific type of metals, which the, I don't know the English word for it. It's steel, I think.
Pardon?
Yeah, it's the steel.
Yeah, right. Like, I mean, does it happen to anything other than metals? That's my question. Yes, no, yes, no. Actually, the answer is yes. It happens to things like even like plastics. But usually we usually think of metals because that's the most common issue for us. So when does it happen? When does corrosion happen? Like, what are the conditions for corrosion? Like, whatever comes to your mind. Yes?
Any type of chemical reactions?
Yeah, right. Anything else? Okay. Corrosion of metal occurs when an exposed surface comes in contact with gas or liquid, and the process is accelerated by exposure to conditions like warm temperatures, acids, and salts. So, like there are now two groups, classification and types. Like, can you name me the classifications and types? Like first classification. Like if it seems a bit vague, I'm gonna give you a hint that classification is related to the medium of the corrosion. So, can you now, after this hint, can you name me the classifications? Okay. Statue of Liberty. It obviously has corrosion, right? Where, what is it exposed to? Statue of Liberty. Like the answer is more basic, like air, right? Like so, the first category is atmospheric corrosion. So if we have atmospheric, then we have aqueous. So we've mentioned that the challenge for our subsea production systems, one of the problems was corrosion. So if we have atmospheric corrosion classification, then we have aqueous marine corrosion. And what about the last one? Like, so we have air, water, what is left? Pardon? Soil? I said the answer actually.
Sorry?
Yeah, soil. So, for example, archaeologists find bullets in the places of battles, right? So usually they are not like perfectly as they don't look perfect, right? So they have corrosion. So corrosion also happens in the soil. So these were our classifications. Now what about the types? Anything, any type of corrosion that comes to your mind? It's like two, like most of the corrosion is oxidation, right? General attack corrosion, like it's like general corrosion, like corrosion happens to the whole body, solid substance. If we have general attack, then like this is for the whole body, right? Then we also should have what? Yeah, well, localized. Localized. So, like, there are three types of localized corrosion. These are pitting, crevice corrosion, and filiform corrosion. Pitting happens when there is a hole, small hole in the metal, and the corrosion breaches the metal and starts to spread and deteriorates the properties and causes crackings and whatever. What else? Crevice corrosion frequently happens in the stagnant microenvironment, like under beneath the gasket or clamps, and can be caused by acidity or oxygen depletion inside the crevice. And the third one is filiform. This happens when water breaches the coating of the metal, and then the corrosion and then it spreads. This usually happens when there are flows in coatings of the metals. Next, galvanic. Can you explain me this kind of corrosion? What is galvanic corrosion? Any suggestion? No? Okay. So the two metals, two separate metals are placed in electrolyte, in the medium of corrosive electrolyte. So what happens is that this creates a galvanic couple between the metals, and so one metal is now cathode and the other one is anode. So now I'm going to say one thing. It's that the metal that is now the anode corrodes quickly, while the cathode corrodes slowly. Like it's the opposite. In the cathode, like there is like almost like no corrosion. What is the reason for that? Like why corrosion is stronger in anode, and on the cathode it doesn't really happen. Like yes. Right, like the oxidation in galvanic cells, the oxidation reaction happens on the electrolyte, on the electrode, which is anode, right? So, and by definition, corrosion was like due to oxidation reactions. So, by logic, on the anode, corrosion should be much stronger. Next one is environmental. So, environmental corrosion is due to environmental factors like temperature, chemicals, and stress. Next one, flow assisted. What is flow assisted corrosion? What is the most common flow in nature for us? The two types of flows. Wind and water, right? So wind and water, they dissolve the protective oxide layer on the metal, and then they start the corrosion starts inside the metal. Next one is intergranular. Can you guess what this means? Okay. Intergranular is due to the impurities in the metal, and so corrosion happens in the grain boundaries. Like this is an interesting one, de-alloying. So what is de-alloying? Like we have alloys, right? And in alloys, like there is a main metal and other chemical elements. So de-alloying means there's no more alloy. So why does this happen? Like corrosion should attack one of the chemical elements inside the alloy. So due to this, like no more alloy. So it's de-alloying. Fretting. Fretting, this one happens when there are two surfaces in contact and there is relative motion between them, and oscillator is usually vibration. So this is due to this. And high temperature corrosion. When does this happen? When do we have high temperatures? What kind of reaction, for example? Release of energy. What is the reaction that releases energy? Yeah, combustion. It happens usually during the combustion. The combustion products cause the corrosion. Okay, so how can we prevent corrosion? What are the ways to prevent corrosion? Yes?
Usually we paint.
Right. That's like the most common, right? What else? Yes?
Create alloys that are less corrosive.
Right. Yeah, right. So environmental modification. This simply means changing the environment of the metal so that the to reduce unwanted chemical reactions and reduce the exposure of the surface to these conditions, like contact with limiting contact with rain or seawater. So metal selection and surface conditions. So understanding the causes of corrosion, like we talked about this here. Why did we need this? Because if we can understand the causes of corrosion, it can lead to selecting proper metals for the particular purpose, right? So this is metal selection and surface conditions. Like there are three ways: cathodic protection, corrosion inhibitors, and plating. Cathodic protection. What is cathodic protection? Like this is an electrochemical process. This is against galvanic corrosion. So we talked about galvanic corrosion, right? Remember? So we said that on the anode there is more corrosion. So we have to obviously protect anode, right? How can we do this? Like, what does cathodic protection do? Like, I think the name says it. Yes?
Ionize the surface to rotate those
Yeah, almost. Yeah, I think yeah, you're close. Like definition of anode and cathode comes from what? What? Yeah, right. And voltage difference causes what? Current, right? So in order to protect anode, we have to create opposing current. So now the anode becomes cathode. So the corrosion doesn't happen. And the next one is corrosion inhibitors. These are chemicals that react with the surface of the metal or with the gas or liquid that is in contact with the metal. So in order to stop corrosion. And plating is just using metallic plating, such as electroplating, that can inhibit corrosion. And the last one is coating. It's applying paints and organic coatings in order to prevent metals from corrosive effects of environment. So I guess this one is the most popular and the easiest one that comes to our minds, right? Yeah, that's it. Thank you.
This is well prepared. Right? And also I found that this can be a good candidate for midterm exam. Right? Many kids raised. So I'll try to make some problem out of it. Once the material is uploaded. But as you may know that my exam is open book, so you can bring. You don't need to memorize all of them. Anyway, I will try to make question out of it. Okay. So this is a schedule. So myself, we will do an ocean renewable energy. And then we know we'll do.
Patrick, you said that the exam is open book.
Yes.
Oh, I didn't know that.
You did? You did not see the sample exam.
I
Yes.
saw
That is shown. Is shown. Or is not written on the exam sheet. Okay.
What we can bring the slides from the class.
Any any material. Only thing you cannot do is discussion, right? Natural. So you can do anything. So it's open. Okay.
Can we use the electronic version of the slides?
Oh yes, yes. But do not talk with friends outside. It's through SNS. Right? That's also prohibited. Right? No discussion in any form, right? That is only restriction. Yes, yes.
이메일 타임.
It's same as class time. Usually I try to, I'm not sure, but I try to give you more problem than time. Because it's open book, so you should be prepared. Right? That is my policy. So it can be an easy, usually easy problem, but many problems. Right? So once you are prepared means you understand the material. So I'm saying coverage is all class, including discussion, right? I've tried to make a problem out of this, all materials covered in this class. All right. Renewable energy first class. So it will be divided into 4 parts, and it was originally prepared by Professor Lee in ocean engineering, but I used this one. So the next time it was 2 years more than. So I will cover only wind part today, and we'll cover tidal wave. And then next week we will cover part 2. So you already know that renewable energy coming from natural resource, such as sunlight, wind, and rain, tidal, and waves, and geothermal. So there is all kind of here, starting from sun, and every energy coming from the air. So you can see that there is a big amount of energy. Half of them from sun, but it is not easy. And raining and water, so hydroelectric power, right? And also wind power. Wind is blowing, and wave here, tidal energy, and radiation, solar radiation. So wind energy. Wind resources. The sun gives all the powers, all the energies, big number, big 11 hours, and to the earth per hour. This is only per hour, so very big number. Energy is coming, and wind is a byproduct of solar energy. All the energy is coming. Approximately 2%, only 2% of this number reaching the earth is converted into wind energy. Still, wind energy is only 2%, but still big enough. Right? So another easier example drawing is solar energy converted into 2%, wind energy. No, this one is wind energy, right? Wind energy and geothermal energy and global consumption is only trillion watt, so that this one is big enough if we can convert this one into consumable energy. Right. This is a Far Eastern area. So Japan is here, Korea Peninsula, and China, Russia. And this is a wind map. Also, this is a Korea Peninsula is over there. So wind is good in around Jeju Island and also near the Busan port. So this is a good place for wind energy. Once again, same picture in different form. So when hot is wind is good, blowing around Jeju Island and Busan port. So there are some already wind power system. This looks like Hangwon is in Jeju Island, and Daegwallyeong is in the mountainside, high mountainside. So you see that this is Jeju Island, and high mountains. As I explained before, the size is become growing. Right? That is the limitation to the landside installation. Usually the limitation goes up to 1 megawatt. There's the maximum size usually already installed in South Korea. Many reasons. But main reason coming from land consumption and also noise coming from the system. Why wind power? Good things, the lowest priced. So it's economically comparing to other source, solar or wave and other geothermal, wind is cheaper to convert today technology. And the trend is lightweight, lower solidity and more flexibility, so larger diameter. And passive load relief. This is a very interesting problem. Something like a band twist coupled system. Can you remember when you visit the Eureka building? We had a class once, right? And at the first floor, there's a wind turbine is rotating. Can you remember that? Right. About this size is inside the building, first floor, the wind is rotating. But you may not notice that the blade shape is not straight, a little bit bended. That was one of the research produced, and we call this a BTC blade. When the wind is very high, something like a storm is coming, and then the wind speed is too high that the design condition is exceeded. What happened with the high wind coming to the in the power system? The blade can be break because of the too high speed of wind. Right? So what can be the measure at that time? Because sometimes it is coming. Typhoon is coming to the Korea in the summer time, several times. Right? So they usually do by rotating the blade so that they change the angle of attack to reduce. So maybe you can use, say, wind is when they rotate, they usually facing. You can expect the wind blow. The face is facing toward you, right? To produce wind to the body. So same as the wind rotating in this way. But if you rotate in this way, then very small effect to the blade, right? Even though wind is coming. So by twisting or angle of attack, they can relieve. So this is a load relief mechanism. But Now they are saying it is active rotation, active control. Right? When the wind is high, they control the blade's orientation by motor at the hub side, controlling pitch angle, right? Or angle of attack. But this one, the system you saw in the entrance of the Eureka building, the blade is designed in such a way that they bend naturally. Because of the wind is high, the system is bent in this direction so that automatically angle of attack is reduced. That is the trend in new design. Passive load relief or British blade. So they do not use motor there to rotate this. The more critical problem is the sensor system. When the high wind is coming, they should sense and then control. Right? The control loop. But if you have a passive control, you don't need such a system. Naturally, they bend to rotate the blade and rotate. Right, and material for blade, and then Europe is more installation, right? But Asia is increasing, and North America is increasing fastly, and it's a little bit old date, 10 years old. Internet. Right, the mechanism is, you see that this is blade, and there is a tower, and this is a generator here inside. So we call this a nutshell, a room, big room, right? Generator room. So inflow of wind, and then inflow of wind will activate a blade, so blade is rotating. Rotation is going into shaft. Rotor, blade, and rotor spin the main shaft, and gearbox to increase RPM, right? The RPM is slow for the whole blade system. So increase the RPM, then generate electricity. And electricity go down to this. So it's a gearbox and generator. Right? Simple. And orientation. Usually you expect this, we call this a horizontal axis in the power system. Horizontal axis. This is a horizontal. Horizontal parallel with the wind direction. Right? Direction. So we call this is a horizontal system, horizontal axis. But there is also another type, vertical axis. Wind is blowing this way. So axis is a vertical. But nowadays this is more popular. Right, size 10 megawatt. 10 megawatt, diameter is 180 meter. 180 meter. How tall is the building? How tall is the building? Five floor, right? 5 meter, 25. This building, 25 meter. 25 is only 100 kilowatts, the diameter of blade. Right? So this building size of our blade is rotating, generate only 100 or 300 kilowatts. But 180 meter is rotating. 180 meter is how many floors there? 36 floor building, right? It's rotating. So bigger, so that they cannot accommodate in the land side. They should put into the ocean. One more, 20 megawatts. This is the current situation is this one is commercialized already. You can buy if you have money. You can buy from company of this size. This one is on the edge of commercialization. So this within 1 or 2 years, you can buy this size. Right? So big one, diameter. This is a only under development stage, 20 megawatts, 300 meter, right? 208, bigger. And size of turbine, small, 10 kilowatt, 100 kilowatt. So they can use for the home, only single home, or pumping, ice making, telecommunication side. But this is for village, whole village, small village, or hybrid means combined with the solar and wind and wave. And, remote site of islands where there is no cable coming from the mainland. They need some kind of self-generation of electricity. And there they use a hybrid system. Why? Because wind blowing, not always, right? Not 24 hours they blows, but not always. Sunshine, only say less than 10 hours, right? Sunshine. Other mechanism too. So that they need to have a steady flow of electricity. So they need collect electricity through solar, wind, and other sources, and then you also need a good storage system, battery, big battery. They call it hybrid system. Large, 5 megawatt. Good. Question? No. So we cannot do discussion today, but anyway, second lecture, please. No, another lecture. We still have us 15 minutes, right?
Okay, so I'll start the second part of the ocean renewable energy, and the energy sources that I will cover is the tidal, wave, and somewhat related. I just named it flow, but yeah, okay, so I'll cover the three renewable energy sources. So tidal energy is using tide energy, and the characteristics are the concentration of the tidal energy is mostly on the bays, open to the west and the east. And the straits connecting two seas, the straits are small gaps between the land masses that connects the other seas or oceans. The one of the straits that we can find nearby is the Hokkaido in Japan, between the Hokkaido and the mainland of the Japan. And also the tune of resonance is effective because the tidal energy has a very the tide has a very constant frequency, and this is related to the predictable power output. So because we know how much tide comes in and how much tide comes out, it is quite easy to predict how much of the power we can produce. So yeah, also relate to what the professor mentioned earlier, it is quite easy to mix with other energy resources. And yeah, so how do we no, why do we have tides? Tide is formed because of the gravitational interaction between the moon, the sun, and the earth, mainly because of the moon. And here it says that the solar tidal force is 46% of the lunar tidal force. So because the earth orbits the sun, it it keeps on gets the gravitational attraction from the sun, and as the moon orbits around the earth, the the ocean part that is near the moon becomes higher. Uh, yeah, so the types of tides, we have the flood tide and the ebb tide. So flood tide is when the ocean water comes into the land, and ebb tide is when it goes out. So the generation of the tidal energy is usually done by blocking the water path between this flood tide and the ebb tide. So considering we have a flood tide at some point, we block the passage, and then we have considerably higher tide at the inside and lower tide at the outside. So if we open this turbine channel, then the relative difference in the potential energy induces the flow to come out. And in the situation of the ebb tide, we can also have the tide on the ocean part higher than the tide at the land. So now the flow is inverted, but still it can induce the rotation of the turbines. Yeah, so tidal energy, this is the same concept. We usually have the tidal barrage, dam like, and we use the potential energy difference to induce the flow. And tidal stream capturing, this is not really like this, but since we have the tides, the flow direction is either towards the shore or the inverse direction. So based on the dominant flow direction, we can install these kind of turbines so that when the flow occurs, the turbines will eventually rotate and generate electricity. So that's just the amount of energy that we can get due to the potential energy difference. And these are some of the tidal power dams that are installed in different countries. And yeah, Shiwa is in Korea, and it has well, quite a lot of power output. Yeah, so the next energy that I just added is the flow energy, and mainly using the flow-induced vibration. This is a product or generation concept called the vivace, which is vortex-induced vibration, ACE something. And how it works is when flow passes through a bluff body, the flow induces, the flow creates waves behind the bluff body, and because the waves are produced in a periodic way, the created waves behind, the periodically created waves behind the body induces force or pressure distribution on the body itself, and because it is formed periodically, then the formed pressure distribution starts to induce oscillation on the bluff body. So by using these flow-induced vibration, we can have such kind of a cylinder oscillation or these kind of hydrofoil oscillations, and we can convert the motion into electricity. Yes, this is the Shiva. And wave energy is different from the tide energy. Wave energy uses the momentum of the wave, and because we have such kind of fluctuations, we can install rigid, well, a bit flexible objects on the surface, and because we have the waves, the waves will deform those structures, and the deformations in the structures are then converted to electricity by using sometimes piezoelectric materials or generators at the hinges. And these kind of buoyancy objects can also be used to go up and down following the wave amplitude. And also this is another concept of the wave energy converter. So all of these are, well, installed, but one thing that we should note is that all of these kind of renewable energy sources takes the energy from the nature and convert it into electricity. So because the relative energy that is converted compared with the total energy the environment has is pretty small. So currently we can say that the environmental effect is quite small, but like in the case of dams constructed in the rivers, if we increase the power output of the tidal energy generators like the Shiwa and the other things that I showed you, we cannot really know what the environmental effects are going to happen. So yeah, maybe that can be a challenging research subject to be done. Yeah, so and that's it. Any questions? No? Thank you.
Only 10 minutes. It's very quick. I worried about the remaining time was less. Well, one thing I want to around the whole topic of renewable energy, you should concentrate on the energy density. Should see about what can be the energy density. That gives you economy of comparison between why do you choose one kind of energy depending on the energy density. Usually the wave energy looks very nice, but energy density is generally low. That's why we do not see many of that wave energy converter. If you have a high wave, then it can be a density. Density means energy per unit size, something like a unit volume or unit area, right? The solar energy may be per square centimeter, something. How many electricity you can get? That is a energy density, right? So probably around noontime, the sun is high, and also at the summertime, solar energy is big, so that energy density is higher there at that time, right? But in the evening or early morning, it was low. So energy density gives you more economy. And then wind and solar is now popular because they are good for the energy density. So you should pay attention to that kind of point throughout the renewable energy. All right, see you next Monday.
이거를 지금 케이블 연결해서 교수님 화면 쓰실 때 이 모니터를 출력하는 거예요. 그거를 나중에 제가 연결해서 만약에 이 모니터로 된다고 하면 그 모니터
아니야, 여기
나중에 제가 한번 테스트 해보겠습니다. 번갈아 가면서
그걸 다 하려면 여기도 그걸 설치해서 쉐어링을 해줘야 돼.
그렇게 할 수도 있는데 만약에 이거를 쭉 하시면
여기서 그냥 다 컨트롤하게.
그냥 할 수만 있으면 그게
그런 방법도 있는데 여기서 투머치만 더 차라리
일단 녹화된 거는 저번보다 많이 개선된 것 같은데 나중에 한번 동영상으로 확인해 보고 그래서 좀 더 개선을 한번
두 개를 나란히 우선.
네, 알겠습니다.